This is what we were discussing last time. How to obtain phasor for a time varying signal. We have gone through this several times in other courses also. You basically write the phasor of this waveform by using Vm and phi v. Oh, sorry, theta v. As simple as that. Okay. Now, this is something that we did last time. You have the document, I think. For voltage and current, the situation is the same when it comes to defining phasors. We looked at time varying. Okay, that we did in the previous document, time varying power. And time varying power can be converted to phasor representation of power also, which is something that I am coming to very soon. In this course, the focus is mostly on power, but voltage and current are the prerequisites. Now, writing the phasors for various kinds of AC signals is an exercise you must be very comfortable with. And here are some problems along with solutions. I am hoping that you will be able to solve all of them without my help. Okay. So please complete this exercise by yourself. This document is already with you. I want to move to the next one, which is not shown to you yet. And again, a lot of things here are well known to you. So we will not waste too much time in doing everything from the beginning. As you know, in a purely resistive load, if you supply an AC power, a single phase AC power, without worrying about time domain, what we do is we write the phasors, and that is probably not that difficult even in time domain, but let's say that we are now going to work with frequency domain throughout, unless there are special circumstances for doing the other thing. So in phasor domain, Ohm's law applies in complex plane. Complex current is complex voltage divided by resistance. Resistance, of course, is a real number. And power, we have already seen the average power is Vrms multiplied by Irms. We saw that in the previous documents. Now, at this point, I need to bring in another concept, which is actually fundamental to this course, that probably is known to you again, but let me reiterate this. There is a concept called complex power, which essentially is the phasor domain representation of the fact that the instantaneous power has a constant part as well as a time varying part. That fact is captured in phasor domain by using a concept called complex power. We will represent complex power by capital S, and we would define it as 1/2 multiplied by phasor for the voltage across the load and phasor for the current in the load, but with complex conjugate. Half will not be necessary. 1/2 will not be necessary if you are using RMS values for phasors. That's what many books do. They use RMS values for phasors and they remove half in the definition of complex power. I would, however, stick to the older method where 1/2 or half is mentioned, and we assume that V and I are phasors in terms of peak values of the instantaneous signal. Okay, this is the very definition of S for all AC circuits. V is the phasor representation of the current in the load. I is the phasor representation of the voltage across the load. V is obviously going to be written in general as Vm e to the power j, some phase angle, which we are going to call theta V. Current in case of a purely resistive load will be V divided by R, which can be represented as Im e to the power j theta I, where Im is Vm upon R and theta I is going to be the same as theta V, because it's a purely resistive load. So it's a very simple case. In this case, if you calculate S, it will be half V into I complex conjugate. So half into Vm into e to the power j theta V into Im into a to the power minus j theta I. Because complex conjugate of Im e to the power j theta I is Im e to the power minus j theta I. Im is a real number, of course. This is how you will write complex, or this is how you'll write complex power in this particular case. And of course, because theta V in this case happens to be same as theta I, you simply get Vm Im divided by 2 as the answer. And Vm divided by square root of 2 is Vrms, Im divided by square root of 2 is Irms. So complex power can be written as Vrms into Irms, which is actually the same as the average power in this case. So purely resistive circuit actually has a simple answer. The complex power is also a purely real number. Okay. Now, one numerical example on this. An AC voltage of 200 cos omega t volts is applied across a 10 ohm resistor. Calculate the complex power generated in the load. There is no phase shift in the voltage. It's 0-degree phase shift. So phasor will be 200 volts. E to the power J0 is understood, which means 1 anyway. Current would be V divided by R. R is 10 ohm, so current will be 20 e to the power J0 amperes. S is supposed to be half 200 e to the power J0 multiplied by 20 e to the power minus J0. So e to the power J0 and e to the power minus J0 anyway do not matter. So the complex power in this case is simply 200 multiplied by 20 divided by 2. So 2000 watts, which is 2 kilowatts. Simple answer. You could also have done it using the formula Vrms Irms. Vrms is 200 divided by square root of 2 volts. Irms is Vrms divided by R. So 20 divided by square root of 2 amperes. Multiply the 2, you should get the same answer. Now, slightly more interesting cases. Purely inductive load in frequency domain. The time domain formula is well known to you. In frequency domain, what we do is, because e to the power j omega t type of time dependence is assumed, d by dt is replaced by j omega. So equation 12 in phasor domain becomes v equal to a j omega L into I, where V and I are the phasors of voltage and current. Differential coefficient is gone in the process. As usual, we define omega L as the reactance of the inductor, which is 2 pi FL. So V is simply JXL into I. And we define V upon I as the impedance of the circuit. The unit, of course, is ohm. And in general, impedance is a complex number. Okay. So the formula for impedance in this case is V upon I, which is equal to simply JXL, which is J omega L and J 2 pi FL and so on. You know all this. Now, complex power in a purely inductive circuit. Let's see what happens to that. 1 by 2 multiplied by V multiplied by complex conjugate of I. V is V. I is V upon Z, right? So complex conjugate of I will be V complex conjugate divided by Z complex conjugate. Of course, in this case, it's not that difficult because Z is purely imaginary anyway. V multiplied by complex conjugate of V gives you magnitude of V square, right? So formula for complex power in this case is magnitude of V squared divided by 2 times complex conjugate of the impedance. Z is purely imaginary. So S would also be purely imaginary, right? Complex power has no real part in this case. What this corresponds to is the fact that no power is being consumed in this circuit. Just live with that for now. In case of a purely capacitive load, also you can do the same exercise by using the basic definition for I as C dV by dt, convert it into phasor domain, which means I equal to j omega C into V. Xc is 1 upon omega C. Using that, Z turns out to be minus j upon Xc. It's a purely imaginary number in this case also, but with a minus sign. Complex power in this case can be written like we did for inductor. Same formula as before, but now Z is negative j something. However, complex power would again be purely imaginary. That means no consumption of power would occur in a purely capacitive circuit also. As simple as that. Now let's go to a real life situation, RLC circuit, which is actually more what you see in real world. What happens here? Other cases are particular cases of this one anyway. Resistance R plus JXL minus J upon XC will be the total impedance. You know this very well. Okay. The voltage, let's say in phasor domain, is Vm multiplied by e to the power j theta v. And let's say the current is Im e to the power j theta I, where now theta v and theta I need not be equal, for sure. That will depend on what the values of RLC are. So let's look at the fact that V upon I is Z. That means V upon I is R plus JXL minus JXC. Remember, XL and XC are real numbers. JXL is the impedance of the inductor. JXC, actually minus JXC, is the impedance of the capacitor. But XL and XC themselves are not imaginary numbers. They are real numbers. They are reactances. So the impedance of the circuit in polar form can be written as magnitude of Z multiplied by e to the power j phi, where magnitude of Z is obviously R square plus J times XL minus XC whole square and square root. We have done this several times. Phi is tan inverse XL minus XC divided by R. Okay, this is load angle. We also call it power factor angle. I'll come to that in a minute. Yeah, actually it's written right here. Phi is known as the angle of the load or load angle. It is also known as power factor angle. Why? We'll come to it soon. Complex power in a series RLC circuit. How would that be written? Half into V into complex conjugate of I. Now pay attention. This is where it starts becoming slightly different from what we have seen so far. Current is V divided by Z. That means Vm e to the power j theta V divided by magnitude of Z e to the power j phi. And current as a general expression is Im e to the power j theta I. If you compare the two, Im is Vm divided by magnitude of Z. Theta I is theta V minus phi. The phase angle of current is phase angle of voltage minus load angle. In other words, theta V minus theta I is phi. The angular difference between the two phase shifts is equal to the phase shift produced by the load, which is common sense anyway. So now try to look at the complex power. Half V into I complex conjugate. here. Half Vm e to the power j theta v multiplied by half Im e to the power minus j theta I. Right? I'm multiplying the two to get Vm Im divided by 2 e to the power j theta v minus theta I. And theta v minus theta I is phi. So the complex power in a series RLC circuit is Vm Im divided by 2 multiplied by e to the power j phi. Vm divided by square root of 2 is Vrms. Im divided by square root of 2 is Irms. There's a bit of typo here. Just excuse me for that. This should be Irms, not Irm. So complex power in a series RLC circuit is Vrms Irms e to the power j phi. It's not purely imaginary or purely real now. E to the power j phi is cos phi plus j sin phi, right? If I decide to write the complex power as P plus JQ, I would get P equal to Vrms Irms cos phi and Q equal to Vrms Irms sin phi, which can also be written as Vm Im by 2 in both cases. Now this is where you have to be very careful about units. P is always expressed in watts. Q is an imaginary power. It is known as reactive power. It essentially captures the fact that some part of the power is oscillating all the time in the time domain. That is being represented by the imaginary part of S. The unit for Q is not watt. It is VAR, volt ampere reactive, just to make it different from the unit for P. Mathematics is not different. It is the way you write units that will be different. For Q, you will never say watt. Watt is reserved for actual power that does some work. Heat, light, etc. are produced because of that. Q is a reactive power that does no useful work. It simply goes back and forth between source and load. But you got to be aware of how big or how small it is. And the total P plus JQ is given another unit called VA, voltage ampere. P is known as active power or consumed power or real power or average power, so many different names. Q is known as reactive power or imaginary power, non-real power if you want. And S is known as complex power, which is P plus JQ. These are the kind of things we will be doing a lot in this course. Q is measured in volt ampere reactive, VAR. P is measured in simply watts. S is measured in VA. S would be in general a complex number. P would be a real number. And JQ would be an imaginary number. Cos phi is known as load angle or power factor angle. Cos phi is known as power factor of the circuit. It basically tells you how much of the power is being converted to actual work. Maximum value of power factor is 1. Minimum is 0. When the load is purely resistive, power factor is 1. That means phi is 0. That means there is no phase shift between voltage and current in the load. If load is purely inductive, phi would be theta v minus theta I. Phi would be minus 90 degrees. And if load is purely capacitive, phi will be plus 90 degrees. In any case, cos phi will be 0. So for purely inductive or purely reactive loads, power factor is 0. For purely resistive load, it is 1. For everything else, it is between 0 and 1. You want power factor to be as high as possible, as close as possible to 1 in real life, to avoid wastage of power. Okay. Magnitude of S is known as apparent power. S itself is known as complex power. Now, special cases of series RLC circuit, if L is 0, C is infinity, you can easily work out. Then in that case, you will get a purely resistive load. for which the results are well known, and many other similar cases you can work out. If R is 0, it's a purely, if R is 0 and L is 0, then it's a purely capacitive case, which also we know already about. So the value of phi will be minus 90 degree in that case. If it's a purely it's a purely, if the resistance is 0, then you will have a purely reactive load. In that case also, phi will be, magnitude will be 90 degrees. The sign will be depending on whether load is predominantly capacitive or predominantly inductive. But definitely cos phi will be 0 in that case. Now, another related concept is power triangle, which we draw for most of the equipment. Basically, you take the value of P on the x-axis, value of Q on the y-axis, and then draw the hypotenuse to indicate magnitude of S. It is obvious that magnitude of S is the square root of P square plus Q square. And phi, the load angle or power factor angle, is simply tan inverse Q divided by P. So these are some of the terminologies that you should be getting very familiar with. As we go along, we'll see more and more of these kind of things coming to you. Now, before I go to my own notes, one PPT which captures all this in a slightly different manner. It's taken from a book. I forgot the name of the author of this book. Actually, yeah, the name is here. Sadiku's book. 5 minutes on this. It's a review of what we have done in single phase AC circuits right now, so far at least. You can read it yourself. Remember, impedance is one thing, admittance is another thing. Admittance is also a complex number. It is 1 upon impedance. Impedance is voltage divided by current. Admittance is current divided by voltage. And obviously, Z and Y are inverse of each other. In many cases, we use admittance instead of impedance. As we go along, looking at specific equipment analysis, you will see that I'll be talking about admittance also in some cases. So be aware that admittance is 1 divided by impedance. Alternating current or AC, all this is well known to you. AC is better than DC, although today people are questioning that assumption, but by and large, I think there is truth in it. Sinusoids means equations involving sine or cosine functions. They capture a lot of natural phenomena. That's why these functions are commonly seen in analysis. And they are relatively easy also to handle mathematically. Fourier series allows you to express any general or periodic function in terms of sine and cosine functions. So if you know the analysis in terms of sine and cosine functions, any general periodic function can also be handled. That's the reason why sine and cosine functions are commonly seen in AC circuit analysis. Transient behavior, you know very well. You have seen in first year and second year courses. That's the short-term effect of application of AC signal. And steady state response is the one which is seen after sufficient time has elapsed. In power systems, we will be worrying about transient behavior, but not right away, much later. This is the formula. He is using sine omega t. I generally use cos omega t, not a big issue anyway. Time period is 2 pi divided by omega, well known to you. Frequency is cycles per second or hertz. This is the last time I'm going through basics. Okay. After that, no more. Angular frequency and frequency, don't confuse the two things. Angular frequency is 2 pi f. Units are radian per second. This is the general formula for time varying voltage signal. I was using cos in my notes, not a big issue anyway. Okay, this is all well known to you. Let's move forward quickly. Depending on the value of the phase, I'm using theta v or theta I, not phi. So be aware of different notations in this PPT. Depending on the phase angle, the waveform may or may not begin at 0 when time is 0. Okay. Simple numerical example. You are given a sinusoid 5 sine 4 pi t minus 60 degrees. Calculate its amplitude. Obviously, amplitude is 5 volts, assuming that the units are volts here. Phase is minus 60 degrees. You can see it. Angular frequency is 4 pi radians per second, right? Period will be 2 pi upon omega. So 2 pi divided by 4 pi seconds, and 1 upon time period will be frequency. All these answers are given right here. You should be able to work them out quickly anytime. Okay. If two sinusoids are in phase, you know all this. Let's not waste too much time going through what you know. Complex numbers. I have told you all this in my own notes as well. Polar form versus rectangular form. What I find is that if you have to multiply two complex numbers, it is better to use polar form. And also, if you have to divide one complex number by another complex number, it is better to use polar form. But for summation and subtraction, Cartesian forms are better. But it's your choice. I'm not going to force you either way. Yeah, well-known things. Yeah, this is elementary complex algebra. When you divide one complex number by another complex number, the phases get subtracted. When you multiply, they get added. Right? Be mindful of all this when you do calculations in this course. Phasors, I have already explained. They are complex plane representation of time varying signals. Here is a formal definition. Phasor is a complex number that represents the amplitude and phase of a sinusoid. Okay, some examples similar to what I have given in my notes. See whether you can make sense out of this or not. Complex numbers are given, figure out the solution. It will require you some time before you get to the answer, but make sure you do it once you get the PPT. These are skills that you will need in the rest of the course to be able to evaluate complex mathematical expressions. Yeah, probably this will require about 10 minutes of your time to complete this exercise. I hope there is no mistake in the answers. I have not double checked the answers, by the way. So if they are wrong, let me know. Important thing is that, in A, you have got two numbers multiplied. It's better to convert each of them in polar form and then multiply. Or if you want, you can do otherwise also. I'm okay either way. Then you'll get something in rectangular form, and then you have to subtract from it something which is in polar form. So this polar form, 5 with an angle of 60 degree, may be better if you convert it into rectangular form first. Then subtraction will be easy. This is my advice anyway. In B also, whatever you have got in the numerator, convert that into polar form, and whatever you have got in the denominator, convert that also in polar form, then do the division. Then convert the result into rectangular form, and the second term is also polar form, convert that also in rectangular form, then add the results. You cannot add complex numbers in polar form or subtract them in polar form. You have to convert them into rectangular form. So I hope you know all this, but I'm reminding you basically. That's it. Okay. Yeah, again, I have got many similar examples in my own notes, but here it's good that answers are given. You can go through these exercises to make sure that you are ready for the rest of the course. Yeah, let's make sure. If you have any difficulty with any of these results, we can talk later after the class also. Now what? What else are they talking about? Yeah, we have seen all this. In case of an inductor, the voltage leads, that means current lags by 90 degrees. We have gone through this. In case of capacitor, it's the other way around. By the way, when you mention power factor of a circuit, generally it is also mentioned along with the value whether current is leading or lagging. If the current leads, we say power factor is leading. That is how industry talks. Leading power factor, that means current is leading. Lagging power factor means current is lagging. Nobody will mention that current word all the time. Then they assume that you know. Leading power factor means current is leading the voltage. Lagging power factor means current is lagging the voltage. Okay, basic laws again. Yeah, we have done something similar in my notes, but just to complete. Yeah, impedance and admittance. Be aware, admittance has something which is opposite of impedance, 1 upon impedance. The unit for admittance is mho, MHO, or ohm inverse. Okay, hopefully this is going to be over. Oh yeah, one more thing. Impedance has got real part which is known as resistance, imaginary part which is known as reactance. Admittance has a real part which is known as conductance and an imaginary part which is known as susceptance. I hope they are mentioning it somewhere. If not, we'll come to it when necessary. Lot of solved examples, basic circuit theory, Kirchhoff's law, etc. I don't think you want to go through. You know all this. Let me just complete this PPT. Yeah, done. One thing, yeah, at the end, they are talking about something which I'll tell you when we go to three-phase circuits. Delta Y and Y delta transformations are extremely critical when we talk about three-phase systems, which probably we will not be able to start today, but from the next lecture, they will definitely be taken seriously. Okay, so this PPT is almost done. Now let's look at some solved problems, simple ones again. Read this carefully. The ratings displayed on the nameplate of a water heater are operating voltage equal to 220 volt, operating frequency equal to 50 cycles per second, and power rating equal to 10 kilowatt. Water heater is almost purely resistive load, okay? No inductance, no capacitance. So power factor is 1. That means phase difference between voltage and current is 0 almost. Calculate the resistance of the heating element inside the heater, assuming that only one element is being used. 10 kilowatt is simply V into I, assuming that the value of voltage given is RMS value, which is the case by default. If the value is 220 volt, that divided by R, which is unknown, will be the current, right? So 220 multiplied by 220 divided by R should be equal to 10 kilowatt. That means 10,000 watt. You solve that equation to figure out R. Frequency information is not necessary for this calculation. Here is the answer for that. Okay, here what I have done is I have assumed that wattage value divided by voltage value will give you current. That is also possible. That's another way of looking at watt. So that gives me current of 45.4545 amperes approximately. I divide 220 by that number to get the resistance value as 4.84. That's another way of doing it. You will get the same answer approximately. Second problem here is your basic understanding of AC signals. The AC waveform shown below is known to complete 600 full cycles per minute. That means 10 cycles per second, right? The peak to peak value is 20 amperes. Okay, so it's current. Okay, fine. Calculate the angular frequency, the time period, the RMS value, the average value, and the form factor. The form factor is defined as the ratio of RMS value and average value. Let's see one by one. Frequency is 600 per minute divided by 60 to get 10 cycles per second. That is frequency, 10 hertz. 2 pi into 10 will give you angular frequency. Yeah, 2 pi into 10 gives you about 62.8 radian per second. That's correct. Time period is 1 upon frequency. Frequency is 10, so 1 upon 10 seconds gives you 100 milliseconds. That is also correct. RMS value is peak value divided by square root of 2. Peak to peak value is given as 20 amperes. So peak value, assuming symmetric behavior, which is shown anyway. Symmetric behavior means top half value is same as bottom half value. So peak value is 10 amperes. 10 amperes. 10 divided by square root of 2 will be the RMS value. 7.07 amperes. Yes, that's correct. Average value we have seen in previous lecture. Over a full cycle, average value is 0. And I guess that is what they want. So, yeah, 0. And form factor is RMS value divided by average value. So because average value is 0, the form factor is infinity. Okay, simple example. Second set of solved problems, let's see what it has. Oh, okay. Again, simple AC calculations. Calculate the reactance of a 1 millifarad capacitor at an operating frequency of 50 hertz. So 1 upon 2 pi FC. 1 upon 2 pi into 50 into C. C is 10 to the power minus 3. So if you do that calculation, you should get this value, 3.18310. Complete this when you get the document. Second problem says calculate the reactance of a 10 millihenry inductor at an operating frequency of 50 hertz. You see, all this was done with mechanical engineering students in mind. So I'm sure you are getting bored, but let's go get it over with quickly so that we can get to real work. 10 millihenry inductor, 2 pi FL. 2 pi into 50 into 10 to the power minus 3 into 10, right? Yeah. So hopefully you'll get this answer, 3.14160 in this case. Never say that reactance is imaginary. It is not. It's a real number. It is J times that reactance or minus J times that reactance, which is the impedance, which has to be imaginary. Third question. Calculate the impedance of a series RLC circuit containing 10 ohm resistor, 3 millihenry inductor, and 5 millifarad capacitor. Assume that the operating frequency is 1 kilohertz. Okay, R is 10 ohm, right? Let's say. Yeah, 10 ohm. 10 millihenry inductor gives you XL equal to 18.85 ohm almost. You can double check the calculations. XC is going to be dependent on 5 millifarad capacitor. I've done that. I've hopefully no mistake in my calculations. XC works out to 0.03183 ohm. So the total impedance will be R plus J times XL minus XC. So J times 18.8496 minus 0.03183. Oh, complex number, of course. So total impedance is 10 plus J 18.8178. In polar form, what you will do is you'll take 10 square plus 18.8178 square and square root the whole thing. You'll get around 21.31 ohm. And you will take tan inverse of 18.8178 divided by 10 and convert the answer. Be very careful. The calculators, some of them are set to radians by default, and some of them are set to degrees by default. Be very careful when doing calculations. This course will require you to do a lot of calculations, not just the theory. I want you to be aware of what your calculator is doing. Is it dealing with degrees or radians? If not sure, do a sample calculation before doing the actual calculation. Tan inverse of 1, does it give you 45 on the result or does it give you pi by 4? If it gives 45, that means you are operating in degrees. If it is giving other thing, then it means your calculator is by default set to radian mode. Anyway, here the answer should be, for the impedance at least, the answer will be 21.31 ohm and an angle of 62.01 degrees. Okay. Let's see what else. Yeah, frequency was 1 kilohertz, which we have used. Now, the last question in this exercise is, if this series circuit is connected across a 10 volt 60 hertz source. 10 volt is RMS value by default. And by the way, frequency is not 1 kilohertz in example 4. It is now 60 hertz. How much current would flow and how much active power and how much reactive power would be generated? This is a very good question. Other questions for just the background for this. You have to calculate the impedance of the circuit first at 60 hertz. I'll give you the solution. Okay, I have not done the actual calculation in my answer, but you should be able to repeat this calculation for impedance by making the frequency 60 hertz instead of 1 kilohertz. In example 3, it was 1 kilohertz. Now repeat the calculation at 60 hertz and calculate the impedance of the circuit, which I hope my answer is not wrong. Then you will get magnitude of Z at 60 hertz as 10.018 ohm and phi, the load angle, as 3.4365 degrees. So power factor is cos of 3.4365 degrees, which is around 0.9982. It's very close to 1. So we should be very happy with this load. Okay. So what do they want? Power factor is one thing. How much active power and how much reactive power is being produced? Okay, that is the question. Active power is simply Vrms, Irms, cos phi. We have seen that in the derivations for a series RLC circuit. Vrms is given as 10 volt. Irms will be 10 volt divided by magnitude of Z, which is 10.018 ohm. And cos phi, we have already calculated as 0.9982. So you put the values. The active power turns out to be 9.964 watts approximately. It is also called real power, okay, or average power. Reactive power is Vrms, Irms, sin phi. Now be careful. Phi is 3.4365 degrees. Take sine of that. The sin phi value would be very small. And not only that, the units for reactive power are not watts, they are VAR. Reactive power turns out to be, double check my values when you get the document. Reactive power should turn out to be 0.5983 VAR. while the active power was 9.964 watts. Reactive power is quite small actually, which is good, which is what we want to see. No wastage of power. Now complex power is P plus JQ. So 9.964 plus J times 0.5983. That is the complex power. And the unit for complex power is VA. I forgot to mention it here, but it's written at the bottom. Apparent power is magnitude of S. That means magnitude of complex power. So take the magnitude of 9.964 plus J 0.5983. You will get around 9.9819 VA. This is how this exercise is completed. Actually, sorry, my mistake. In the solution, the pages have been turned around. Calculation of Z is shown here. Yeah, okay, my mistake. Sorry, the pages are flipped. This page should have been there before that page. This is how impedance has been calculated. Yes. XL turns out to be 1.131 ohm at 60 hertz. XC turns out to be 0.5305 ohm. Okay. So Z is R plus JXL minus JXC. It turns out to be 10 plus J times 0.6005 ohm, which in polar form is what I had assumed here. Yeah, fine. Okay. So these are the kind of things in single phase circuits that you should feel reasonably comfortable with. Let me see something else. I don't think I want to waste too much of your time on single phase circuits, but I'll send you this document. There's a lot of numerical problems on single phase circuits here, starting with time domain and then going to phasors. This gentleman has made some corrections also to his notes. I will not vouch for accuracy of everything, but these are good questions. There's a lot of them. Oh, by the way, before I tell you this, it is also important when you do these kind of exercises to be able to draw the power diagram. Okay, power triangle rather. For instance, here, let me go back to this one for a minute. In the last problem, we found P as 9.964 watts, Q as 0.5983. So if I ask you to draw a power triangle, on the horizontal line, you will draw a line approximately representing 9.964 watt. On the vertical, you will draw a small line because it is supposed to represent only 0.59 value. So it should be very small compared to the horizontal line. And then you join the hypotenuse, make the hypotenuse between the two. By the way, Q can be negative also, although in this case it is not. Sin phi can be negative also. Cos phi is always positive, but sin phi is not. So if phi were negative, you would have got a negative Q. Is it possible? Then the power triangle will have the vertical side going downwards. I'll show that in other examples later. Don't assume that Q would always be negative. Oh, Q would always be positive. That's not true. Okay. So just 1 minute. This one, I think we are done with. For reference, you should keep this document. There is no need to solve every problem here. I'm not asking you to do that. Our focus is going to be three-phase circuits anyway, which is where all this will be required. This is also a simple document which repeats what I have told you. Phase, power factors, real, reactive, and apparent power. All these definitions are given by this gentleman also. This is power triangle for a typical case where Q is positive and P, of course, is always positive. There are times when Q can be negative. Then the triangle will be flipped. Go through this example yourself. This, when Q is not zero, that means there is time dependence of power in the time domain. That is what it means. There's a mathematical proof for that. I'm avoiding it for now. Okay, so I think this is almost what I wanted to do for single phase circuits. Now to talk about three-phase. That's the beginning of the course now, really. Okay, let me see. Three-phase means three independent generators, three independent voltage generators, let's say, forget current generators. Three independent voltage generators with 120-degree progressive phase shift between them. One generator with 0-degree phase shift, the next one with minus 120-degree phase shift, and the third one with minus 240-degree phase shift, and connected in a certain manner. That's a three-phase system. You could also have a system where the first generator will have 0-degree phase shift, the second one will have plus 120-degree phase shift, and the third one will have plus 240-degree phase shift. That is also possible. Both are okay. But how to connect them, and this is what actually is done in power generation systems. We don't ever supply power, don't ever use single-phase power transmission, because three-phase power transmission is found to be a lot more economical. For the same amount of effort, you can transmit much higher power. For the same transmission line, for the same amount of poles that you have erected, same amount of money that you have spent on the project, you can transmit much larger power if you were using three-phase systems. That is the motivation why three-phase systems are invariably used for transmission of powers. Theory of single-phase systems, of course, is going to be useful. No issue with that. Okay. I'm trying to open this document. Give me 1 minute. Okay. What happened? I don't know. 1 minute. Okay. Right. Three-phase introduction. Maybe that is a better document to look at. Invariably, the entire world uses three-phase systems to supply bulk power to customers. There were times when people experimented with two-phase systems also. Have two generators connected with some phase shift between them, etc., etc. But it turned out that although theory allowed that possibility, in practice, the amount of effort involved with two-phase systems was not that different from the amount of effort you would need to build three-phase systems. And three-phase systems still have much higher power carrying capacity for the same transmission line. Other advantage of three-phase systems compared to two-phase systems or single-phase systems is that if you do everything right, the oscillatory part of instantaneous power may be made zero, in theory at least. Remember, in single-phase systems, I showed you the instantaneous power having a constant term and a time-dependent term. That situation is very dangerous, as I told you several times. That can actually be avoided in three-phase systems if you do things right. It's not easy, but theory allows it. In single-phase systems, even theory doesn't allow it. So let's look at this document. A three-phase electric power system contains three single-phase generators producing identical sinusoidal voltage waveforms having 120-degree progressive phase shift. That means the difference in phase shift from one generator to other is 120 degree, and from that generator to the next generator is also 120 degree. It's a relative phase shift between the two generators, which is 120 degrees. That means that is what they call progressive phase shift. Almost all electric power generation and transmission in today's world is in the form of three. When I say 3 phi, I mean three phase. Okay. Don't confuse this phi with the power factor angle. This is a symbolic description of three-phase system. Many books say 3 phi, not three phase. Distribution, of course, is where customers are not necessarily demanding three phase anyway. So a lot of distribution is single phase, but generation and transmission is invariably three phase. On the distribution side, transformers are going to give you both three-phase and single-phase voltages. And depending on customer requirements, you may want to give a different thing. Sometimes in the same factory, you will need both single-phase and three-phase supply. Even in homes nowadays, bigger equipment needs three-phase supply. Many homes also are demanding three-phase. So based on that, distribution challenges are very different. Okay, a mixture of three-phase and single-phase is what distribution is all about. If you had started with single-phase system, three-phase would not have been possible at all, even if customer wanted it. But if you have started with three-phase, single-phase can always be derived from the three-phase. You take only one of the outputs instead of three outputs. So it is good that we are starting the generation in three-phase. That way we are remaining open to the possibility of taking care of single-phase demands. Other way around, it's not going to be possible. Okay, power to weight ratio. That means amount of material that you have spent, copper, aluminum, etc., to transmit a certain amount of power. It will have some weight. This is engineering talk. This is not theoreticians talking. These are engineers, real life engineers. Rajasthan Electricity Board engineer or UP Electricity Board engineer. They'll all talk like that. Power to weight ratio. That means how much weight of material I've used versus how much power I'm transmitting. This is how economics are viewed. The higher this ratio, the happier the engineer is, the happier the politicians are actually, because you are transmitting a lot more power without spending too much money. Okay. So power to weight ratio, I'm not going to do theoretical calculations here, but it has been shown that it is much higher in case of a three-phase transmission. Actually, there is a formula which I don't have in this PPT, but there is a mathematical proof for this. But take it from me, that with the same amount of money, if you are building three-phase system, you will be able to transmit a lot more power to society. That's one main reason why three-phase systems are preferred over single-phase systems, at least in generation and transmission. The other advantage I have already told you, the pulsating part of the power can be made zero, at least in theory. We can say that the cost of producing the same amount of electric power goes down significantly. You can Google this question, by what factor does it go down if we go from single phase to three phase? Answers are available, I think, on Google. Okay, so point number 1 and point 2 are same thing, but written in a different language. Transportation cost goes down, of course, because less material is involved. So transportation cost will go down. Maintenance and installation efforts would also be less. Now the fourth one is what I told you already. Very good advantage. Power delivered to a three-phase load is constant at all times, instead of pulsating as it does in case of a single-phase system. Of course, there are a lot of ifs and buts with this, but yeah, theory at least permits this possibility. In a three-phase system, even if one generator fails, you will still be able to supply power because other two generators are operating, right? In a single-phase system, that will not be possible. There will be total darkness in the customer's premises. That's one more advantage, practical advantage. System reliability goes up because of that. A three-phase generator can feed a single-phase load, but the other way around is not possible. So it's good that we are starting with three-phase generators to begin with. Other thing is, in many cases, people want DC supply. It has been shown that if you are using rectifiers, three-phase rectifiers, bridge rectifiers in each phase, for instance, phase means each generator. So if you are using rectification in a three-phase system, the ripple factor is much lower compared to if you were doing the same thing in a single-phase system. That means the filtering, the capacitor value required, and etc., even Zener diode requirements may be much less severe if you are designing a power supply to convert three-phase AC into DC compared to single-phase AC into DC. There's a lot of work here that may be required to prove all this, but let me tell you the final result. This is for sure. The filtering requirements in case of a three-phase AC to DC rectifier are much less severe compared to the same in a single-phase rectifier. Three-phase system. This is what they should look like. Three different voltages, all same waveform, same frequency, but they are starting at different instants of time with zero value. 120-degree phase shift progressively. Each voltage is given the name phase. Phase 1 means generator 1, phase 2 means generator 2, phase 3 means generator 3. There's progressive 120-degree phase shift. Here I am assuming plus 120-degree throughout, which is also okay, nothing wrong with it. What we do is we have three generators which are being shown through these symbols. Is cylinder, on top of it conductors. That's how the rotor of the generator looks like. Okay. So three generators, one end of each connected together as a single node, and the other ends going out to the world, other three ends. The things that public sees are four wires coming out, one from the common point and the three from the other three ends of the generators. These 4 points or these 4 wires are called lines. Public sees lines, they don't see phases. Line means 4 wires coming out from the system. The wire which is coming from the common node is known as neutral wire. There's a reason for it, we'll come to it later. This is one way of connecting generators. This is called Y connection or star connection. You see, because one point is common. One of the terminals from each generator is connected together. This is why it is known as a Y connection. People also call it star connection. And 120-degree phase shift is there. The top one generator will have 0-degree phase shift, let's say. The one on the rightmost bottom will have, say, minus 120-degree phase shift. And the third one will have minus 240-degree phase shift. They can also have 0-degree, plus 120-degree, and plus 240-degree. That is also okay. Nothing wrong with it. This is also same thing. Star connection shown again. Neutral wire is the one coming from the common node, and 3 wires coming from the other ends of the generators are known as lines. Line 1, line 2, line 3, and neutral. In many cases, people avoid neutral. It is a lot of work to maintain neutral, but it is advisable to have neutral available as far as possible. These are not inductors, by the way. Generators typically have inductive behavior. That means their input impedance is highly inductive. That is why instead of drawing signal generators in the diagram, they have shown inductances. These are not passive things. These are actually generators in the 3 arms of the star connection. Okay. Now, another possibility is to connect the 3 generators with no neutral, instead having what they call delta connection. You see the rightmost side. They are connected in tandem. That means one end of a generator is connected to the beginning, to the other end of the other generator. There's no common point here. There's no neutral possible here. This is called delta connection, obviously, because the shape looks like delta. Here also 120-degree phase shift is maintained, but behavior is quite different because of the way the connections have been made for the generators. Here only 3 wires come out and they are known as lines. No neutral is possible for a 3-phase delta system. Star system versus delta system, there are pros and cons. Engineers always debate which one is better. What I know is that in real life, both of them are used depending on the situation involved. So in 3-phase systems, the star connection can be at the generator end, and the load, and the delta connection can also be at the generator end. Even on the load side, the lines ultimately will feed loads, right? Even the loads can be connected in delta form or star form. So power systems conceptually are of 4 types. Let's say star generator, star load, star generator delta load, delta generator star load, and delta generator delta load. Theory allows four possibilities. Engineers prefer one of them or two of them much more than others. That's for sure. I know. My plan is to look at star-star system very carefully, where the generators will be connected in star configuration as well as the load will be connected in star configuration. And after that, I'll try to spend some time on delta-delta system. The other two, delta Y, delta star or star delta, can be analyzed if you know the delta-delta and star-star theory very well. Okay. Here is one example. You have star connected generators, but delta connected load. No neutral is necessary in this case because load doesn't want a neutral. It cannot accommodate a neutral, right? But this is real. In many cases, you will see this in power systems. And by the way, books do not mention it generally. There's besides the neutral wire, there's a fifth wire also sometimes. It is known as ground wire. Neutral in theory can have zero voltage if everything is balanced. That means all arms of the load have identical impedance. All generators have equal output voltage, equal frequency, etc., etc. But that is very difficult to predict in real life. In reality, the neutral may not always be at zero potential. I'll prove it all mathematically later. So to maintain a reference zero voltage throughout the power system, it is highly advised to run a grounded wire also. Maybe it is not there in the transmission lines, but it is definitely there in on the generating side as well as on the substations, where we dig a deep hole in the ground and provide solid grounding to that wire. That ground wire, because we know it for sure will have zero potential no matter how unbalanced the power system has become, that zero potential can be used as a reference for diagnostic purposes and for measurement purposes. So don't confuse ground wire in power systems with neutral wire in the power system. Neutral wire is simply coming out from the common node. Ground wire is actually grounded in the ground, or somehow we make sure it is at zero potential all the time. Generally, we will not talk much about ground wire, at least in theory. Okay, one more example. Here you have star-star connection or Y-Y connection. If Z1, Z2, and Z3 are equal to each other, then it's a balanced load. If they are not, it is unbalanced. And similarly, VAN, VBN, VCN, if they are perfectly equal to each other, then with of course 120-degree phase shift throughout, then it's a balanced generator system. Theory is much more easy when you have balanced systems. Unfortunately, real life is never balanced. We will see how to handle real life. Simulation tools are around to help us in calculations, especially when systems are unbalanced. But for balanced systems, theory is reasonably simple, I think. Last PPT, quickly capturing what we have been talking about. This was actually prepared by a faculty member in mechanical engineering department of our institute. Their mechanical engineers are obsessed with power systems. They do most of the work anyway. So let me quickly rush it through and then we'll stop for today. These are the books, by the way, which are recommended even in the course that I'm teaching you. Thareja especially is a very good book for power systems and for machines as well as for transformers and many other things. I have e-copies of at least Thareja for sure. I'll share it with you someday. For now, whatever I'm sending you is probably okay. Single phase signal, simple enough, only one voltage in phasor form. It has e to the power j omega t type of time dependence. So with time, the phase is continuously changing. So it's a rotary phasor. It's a rotary vector with time. And calculations are extremely simple. You take V divided by Z to calculate the current in complex domain. No issue. Three phase Here, what he's doing is he's showing each phase, that means each generator independently, assuming that the load is balanced. All the arms are equal in impedance. But the voltages have 120-degree phase shift throughout. The the waveforms are going to be shifted by 120 degrees, obviously. Avoid theory right now. We'll do that next time. He's showing you how to do calculations of currents. I'll do it anyway in detail in my own notes. Again, some examples. You have a star system here. Neutral is going from generating station to the load, because it is possible to run in neutral now. Theory, we'll talk here, is showing that the power has no time dependent component. I'll show that later. Good question. Is the neutral line necessary? But in real life it is. In balance system it is not. Oh yeah, other thing, the three lines, the three wires coming out, they are either called phase A, or actually line A is better word. Line A, line B, line C, etc. In many books and in real life also, we say red, yellow, and blue, because the wires are coated with dielectric material, and those dielectric material, that dielectric material is given a certain color to distinguish one line from the other. That is why red color line is called red line, and the yellow colored wire is known as yellow line, and blue color is reserved for the third line, and neutral is generally coated with black material. You have to insulate these wires, so that even if somebody touches them, the effect will not be too dangerous. Of course, transmission lines are generally left unshielded. I mean, we don't put anything on them. They are pure conductors going, because it's very costly to put conductors or to put dielectric over thousands of kilometers of lines. But on the generating side and even on the load side, we try to insulate wires to avoid accidents. So RYB is another notation instead of ABC that we will be using in some cases to describe the phases or the corresponding line wires which are coming out. Yeah, I have told you this already. Y, which is also known as star, and delta. We have seen this diagram already. 2 or 3 more minutes, okay? Yeah, I'll do the analysis later. This is how you write the voltages in phasors. First voltage, VA, and I'm writing small n here to say that this voltage is measured compared to neutral line. Some peak value with 0 degree phase shift. Second voltage with the same peak value but with minus 120 degree phase shift. And the third one, same peak value but with minus 240 degree phase shift. Other possibilities, you can have phase shift 0 degrees plus 120 degrees and plus 240 degrees. That is also okay.